All right, the last thing that's a part of section 5.4 is something called the Net Change Theorem. And the idea here is that the integral of some function that represents a rate of change, that integral is going to give the net change over an interval. So if we're taking the integral on the interval a to b, and we've got something like f prime of x dx. And I'm calling this big F prime because we know that derivatives can be used to represent rates of change. We've seen that on a couple different occasions in a couple different ways in this class. So this is just showing that this is a rate of change of some function big F of x. Okay. So if we're integrating that rate of change, this, all right, if you think back to our fundamental theorem of calculus, part 2, the result for this is really just going to be big F of b minus big F of a, okay? Taking the antiderivative, that would be big F of x, okay? Plugging in your upper limit of integration, subtract, plug in your lower limit of integration. This part over here is giving you the net change, or the change that's occurring in the function big F of x between those two x values, x equals a and x equals b. Okay, so some practical examples here would include things like temperature. All right. If you had a rate of change of temperature, like big T for temperature, and it's changing over time, something like that, okay? So this would be a rate of change, okay, because it's a derivative of temperature. That would be the big T, by the way. And it's changing over time, little t. All right, so if you had an integral like that, and it was between two different t values, little t, we'll call it little t1 and little t2. All right, this would give you the temperature at time t2 minus the temperature at time t1. Okay, so this over here is the change in temperature between those two times. We call that the net change in temperature between time t1 and time t2. Okay, and this idea of net change is that it is just the change looking at only those 2 points. Like, let's say your temperature over time, okay, started with a pretty low temperature, like, I don't know, early in the morning, and then it heated up, and let's say there was like a weird spike in temperature midday or something like that. And then it cooled back down. Okay. If we were looking at times T1 and T2, here and here, the net change in temperature is literally just the difference between those two values. This is big T of T1, this is big T of T2. Okay, so the net change in temperature there is not very much. Even though there was this large change in temperature in the middle of those 2 times, net change just looks at the difference between 2 individual points. Okay. So that's for temperature. The other one that we tend to look at is motion, and that's what our example is going to look at here. So to kind of summarize really quick here for motion, all right, if we integrate between 2 points in time, t1, t2 again, if we're looking at a rate of change here, notice how our problem is going to be looking at position and velocities. So let's look at a rate of change of position. All right, s prime of t dt. But we know that the derivative of position is velocity, so you could integrate your velocity function. That would mean the same thing. So rate of change of position equals velocity. Okay, rate of change of position equals velocity. There we go. But if we look at this in the sense of integrating the derivative of position, that looks like our net change theorem statement here for the position function. So we would take our position function at time t2, s of t2 minus s of t1. And this would give us the net change in position. Like, how far has this object moved between time t1 and t2? Not including what's happening in the middle of the interval, but literally from just its ending position and its starting position. What has changed there? Okay, so our example here says an object moves along a straight line with position function s of t and velocity function v of t. Notice how it's not actually giving us the function equations for those functions, just the names. But we're told that s of 1 equals 12 meters, and the integral from 1 to 4 of v of t dt equals 17, and we want to find s of 4. Okay, so this integral right here is giving us a net change in position. So we're integrating that velocity function. So this is net change in position. That's the 17 there, 17 meters looks like our unit is. All right. So this is showing us that we're integrating from 1 to 4 v of t dt, whatever that function may be. But we know we could also write this as s prime of t because velocity is the derivative of position function. And so according to our net change theorem here, this would be s of t2, which is 4, minus s of t1, which is 1. All right. And we are looking for s of 4, so we'll leave that right here. But we're given the fact that s of 1 equals 12 meters, so let's plug that value in. Okay, so here we have that integral, which equals 17, and the net change theorem tells us that that net change, 17, is s of 4 minus 12, and we can solve for s of 4 really quickly in that way. S of 4 equals 29, and so our position at 4, I'm guessing this is in seconds perhaps, but the position unit here would be in meters. S of 4 equals 29 meters. Okay, So yeah, that integral was telling us how much the object changed its position between 1 second, or time 1, and time 4. Okay, so it went from 12 meters. This shows that we add a net change of 17 meters. And so we end up at S of 4 equals 29 meters. All right, so there's a quick example of the net change theorem. And really all this is just an application of the fundamental theorem part 2.